I don't get it. My pizzas are delicious, my rent is paid, and everyone loves my food. But the shop down the street just closed, and I feel like I'm flying blind. Am I next? Is there any way to avoid? Is there any way to know if my business is actually dying?
Well, did you check your rating volatility?
My what?
Your competitor volume gap? Or your sentiment slope?
I'm a cook, not a mathematician. I just have Google Maps reviews.
Exactly. That's all we need. We don't need your balance sheets. We don't need you to be a mathematician. We can predict if your business is going to fail just by looking at the digital crowd.
Prove it.
Welcome. Our project addresses a critical gap in the business intelligence. Most failure prediction models for businesses rely on private financial data like tax returns, cash flows, which is unavailable to the public.
Our goal was to determine if we could predict permanent closure solely using public metadata and user interaction signals from the 2021 Google Local Reviews dataset.
The dataset contains two files. One contains the metadata for each business. The other has the review history as user business pairings. We processed and combined these two data files to get a combination of business metadata, which includes the location, price, category of the business, and the review history, such as the review text, any photos added to the reviews, ratings, and the timestamps of the reviews. Ultimately, we end up with a set of 45 unique input features. The output is a risk assessment score representing the chance of the business closing, where 0 is fully operational and 1 is permanently closed. We formulated this as a binary classification problem. However, this is an imbalanced classification task. In the dataset, open businesses vastly outnumber closed ones, a ratio of roughly 22:1.
Because of this imbalance, simple accuracy is a trap. A model could predict open 100% of the time and still look accurate. To assess validity, we define success as 1. Beating a dummy baseline, that is random guessing. Second, beating a strong course baseline, in our case, that is logistic regression. 3. High ROC AUC, representing the model's statistical power. 4. High precision at top K, which is an indicator of the model's business utility.
Let's look at the data. The dataset is divided into subsets for each US state. We focused on the Alaska subset for prototyping and scalability testing, as it was the smallest out of all the US states, with 12,000 businesses and 500,000 reviews. After multiple iterations of parameter tuning, once we were satisfied with the results, we finally ran the model again on the New York subset, which was a larger dataset with 270,000 businesses and 18 million reviews. The raw data is massive and formatted as Python eval objects, not strict JSON. We implemented a robust stream parser using ast.literaleval to handle this memory efficiently. Now, this is where our approach differs from standard analysis. We didn't just dump the columns into a model. We engineered features based on business failure theory, divided into four specific prongs. Prong 1 is vital signs. Just like a patient in a hospital, a dying business shows weak pulse. If customers stop posting or the owner stops replying, the business is likely entering a zombie state. We calculated days since last review for recency, a photo rate for quality of reviews, and the owner's response rate. Prong 2 is temporal trajectory. A 3-star rating is bad, but a rating that dropped from 5 to 3 in the last month is even worse. We calculated the slope of ratings over time using linear regression to capture this decline. We also calculated the standard deviation of ratings to understand if the reviews are volatile or stable. Prong 3 is the semantic layer. We used NLP to analyze the average sentiment of the reviews, as well as the sentiment slope, which tells us how customer impressions have changed over time. However, here we use NLP not just for sentiment, but to look for specific death signals. We scanned review text for keywords like boarded up, shut down, or gone. A high ratio of these words is a massive red flag. Until now, we've used TF-IDF in the scores for basic NLP, but here we chose to go with TextBlob instead, an extremely powerful and efficient Python NLP library which improved our code's execution speed and accuracy. Prong 4 is competitor context. A rating of 4 is great for a Taco Bell, but terrible for a Michelin star restaurant. We calculated competitor rating gap and competitor volume ratio to measure how a business performs relative to its local competitors.
For modeling, we compared three approaches. First one being heuristic baselines, simple rules like if rating is less than 2.5, assume closed. Second, logistic regression, the core standard baseline, good for interpretability but assumes linear relationships. Third, XGBoost, that is gradient boosted trees, which is our primary model. We picked XGBoost because business failure is non-linear. For example, a high price is fine if ratings are high, but deadly if ratings are low. Trees capture these interactions naturally. Here's our training pipeline. First, we calculate all of the features from the four prongs mentioned earlier. Then, we add some additional metadata to support the model, starting with price. We convert price from a string to an integer representation. We use multi-label binarizer to one-hot encode categories like restaurant versus dentist. We added latitude and longitude so the model could learn good and bad commercial neighborhoods. We split our data using a 80-20 train test split. We then ran the logistic regression baseline. This required scaling the input, which XGBoost doesn't, storing the results to compare later on. Finally, we ran the XGBoost algorithm along with a custom script to automatically tune the hyperparameters and find the best model. Crucially, we used threefold grid search to train the scale POS weight parameter. This tells the model to pay 20 times more attention to the closed class, counteracting the dataset imbalance.
Now, we moved beyond standard accuracy by performing threshold optimization. Standard machine learning models default to a decision boundary of zero point 0.5, which often fails to detect rare events like business closures in heavily imbalanced datasets. The chart here visualizes the trade off between precision and recall across all possible thresholds. The vertical line marks our calculated optimal boundary at 0.16 for Alaska and an even better 0.25 for New York, the point where the F1 score is maximized. By shifting the sensitivity to this specific frequency, we significantly increased our recall. This allows the model to flag zombie businesses that show subtle signs of failure rather than just waiting for them to be completely dead before detecting them. We then computed the ROC curve based on these thresholds. ROC stands for Receiver Operating Characteristic, which measures the rate of true positives against the false positives. And here's a look at the results. The random guessing model achieved just an area under the curve of zero point 0.5, while the logistic regression achieved an even better curve of zero point 0.7. But our own XGBoost model achieved an ROC area under the curve of zero point 0.91 on the Alaska data and even better 0.95 on the New York data. This ROC curve specifically demonstrates that our model is significantly better than random chance, and linear baseline, distinguishing between open and closed businesses. Now, let's look at what actually kills a business. Looking at the feature importance plot, 3 points stand out. The first one, recency, which is the number one predictor. If people stop talking about you, you're already dead. Second one, price numeric, and it was surprisingly high, showing that expensive places are more fragile. And finally, debt signal ratio, our custom NLP feature, popped as a top predictor. Then, we ran a robustness check called an evaluation study. We asked, what if we hide the dates? Even with our recency data, our NLP and context features maintained an area under the curve of 0.88. This definitely proves that the model isn't just memorizing dates, it's actually understanding the content of the failure. And finally, for the business case, precision at top K. For the Alaska model, if an investor used our model to shortlist the top 10, just the top 10 riskiest businesses, 60% of them were actually closed. Considering the baseline rate was only 4%, this in itself is a massive jump in predictive power. However, the Alaska model showed significant drop off at higher K values. But on the other hand, the New York model, which was trained on almost 22 times the number of data points than the Alaska model, showed significantly more precision, along with a consistent behavior across all K values. For an instance, if an investor used this model to shortlist the top 1,000 riskiest businesses, 90% of them were actually closed.
Briefly discussing related work. Historically, business failure prediction relies on macroeconomic data, GDP, unemployment rates, or financial statements, like the Altman Z score. Our contribution, we shift the focus to crowdsource social signals. Similar work has been done using Yelp data, but focused on ranking restaurants. Our work focuses specifically on the life cycle prediction, treating the business as an organism with health metrics.
Now, all of this is great, but how do we actually make this actionable? A CSV file of probabilities isn't useful to a restaurant owner. So, we built a proof of concept front end tool. Uh, in this tool, it's very simple. A user just types in the name of their business. The system pulls the latest reviews and metadata from the Google dataset, and it feeds this data through a pre-trained XGBoost pipeline. Um, for a quick demonstration, let's say here we search for Joe's Italian Bistro. It analyzes the restaurant data, and you can see it's found it. Just a quick overview of the restaurant to verify that we do have the correct one. And here, the system flags it with a risk score of 68%, which is a very high risk of closure. But more than just a simple risk score, it also highlights why. It gives a breakdown of its entire analysis based on the four prongs that we were discussing earlier. So it talks about the parameters it used, the vital signs, the temporal trajectory, the semantic layer, and the contextual layer. Furthermore, it also gives a breakdown of the rate of its ratings for each prong, along with a simple text description of what each rating stands for. So any business owner can very easily understand where their restaurant is lacking. Is it the response rate? Is it maybe the rating volatility? Or is there a huge gap in between them and their competitors? This turns our black box model into a transparent diagnostic tool for owners. In conclusion, we successfully identified that social signals on Google Maps are highly predictive of business failure. We beat the baselines and built a robust, interpretable model. Future work would involve expanding to the California dataset, which is the largest out of all the United States, and analyzing the text of owner responses to see if defensive replies correlate with closure. Thank you for watching.
Thank you.
Thank you.